thank you. And I'm glad some people are not sick of listening to me this week. Yeah. So also, apologies for this looks pretty. It's sort of going to stop looking terribly pretty because this seems to be the first talk I ever wrote on my tablet, and it's sort of a little shaky. But I'm not. But since we're writing a paper on all the wisdom and the short version, polyfolds for dummies, I'm not going to redo these slides. So hopefully you can read them. Right, so this is a not so new technology anymore by Hofer, Wysotsky, and Zehnder, and I pride myself in actually having understood that it's going to be important some 5 years ago. So let's see. Good. Okay, so this is sort of what we used to do in symplectic topology, what we still successfully do in good cases, where somehow the bubbling doesn't get too wild. So what we usually do is we describe our moduli space of holomorphic curves as the zero set of a section modulo an automorphism group. Right? So in the simplest cases, X is some space of maps to symplectic manifold W. There's a section is the d-bar operator that lends in some bundle of 0, 1 forms. And there's the whole automorphism group of the surface that under which this image, this section is equivariant. Right? And so then what we do is, so that's our description. We have a Fredholm section modulo a usually non-compact Lie group. And there's also a compactified moduli space that people like to think of, but you often, certainly for Floer theory, get away with not actually compactifying the moduli space, but just identifying the ends of the moduli space with some fiber product of lower dimensional moduli spaces. Right? So that gives you algebraic identities like d squared equal to 0 or the A infinity relations. And in order to actually get this algebraic data out of these moduli spaces, there's sort of 2 essential steps that need to be done. We need to find a perturbation of our section that that's transverse to the 0 section. And we need this to still be equivariant and somehow compatible with the gluing. Oh. Sorry. I guess there's a reason I brought the power cord. Okay, let's see. So, I mean, this sort of much belabored fact already in the last couple of talks of Kuranishi structures. To me, there's a oh, and now we changed the settings again, huh?
You have to change your resolution back.
Okay. Sadly. Okay. Let's try that. So what I find rather surprising and magic in symplectic topology is that in rather a lot of cases, we're actually able to find equivariant transverse perturbations, which is something you just wouldn't expect usually. Oh, gone. Okay. Wow. Okay. Good. Right, and in particular, what we usually do is we wiggle on the J, and that really is a perturbation in the highest order of our operator. So from a sort of far away, functional analytic point of view, we're perturbing a first-order operator with a first-order operator. There's no reason why the result should still have the same compactness properties. Right? but it does because they're holomorphic curves, right? And there's a lot of the usual analysis, you know, Sard-Smale, and then we need gluing analysis. Oh, right, compatible with gluing, right? So there's a whole lot of gluing, and I think if you do that lovingly in full detail, you actually need around 100 pages. I've done that once in my life. I really don't feel the need to do that ever again. Yeah. And I personally would write, you know, in the next papers, it works as usual, or in my other paper, or in some other people's paper. But that is not a proof, because, you know, even a smart graduate student might take a couple of years to fill in the details. Right? So it's sort of very little stays quotable when you change your setup a little bit. So that's one defect in my mind, and the other defect is that in order to get an actual smooth structure on the compactified moduli space now, right? So, curly M up here was zero set mod automorphism, and there's some compactification that you can construct from the gluing. You need further constructions. You need coherent perturbations. You need them before also. But you need to really make sure you prove enough gluing to sort of get nice corner structures and, you know, some smoothness in there, and I don't think that's been done anywhere really rigorously, except when your moduli space is one-dimensional. So, and it also, the other defect, I think, is that it just really doesn't use a lot of machinery, a lot of hands-on. We'll use the Sard-Smale theorem, and then mainly it just uses the standard implicit function theorem. You know, we want to make the differential of our section on the zero set surjective, then, you know, the zero set is a smooth manifold of, you know, the dimension given by the Fredholm index. Right? But really, there's sort of a different finite dimensional transversality result that this is really somehow the black box that we'd like to stick our moduli spaces into. Right? Except we only have it in finite dimensions. Right? So we'd like to say there's a section of a bundle, zero set is compact, and then for a generic perturbation, you know, compactly supported near the zero set, you get the, you know, perturbed section transverse to the zero section, so you get a smooth manifold out. You hope it's still compact. Right, it's still going to be compact because P is compactly supported and the zero set was compact. Right. And then if you have two choices of perturbations, you want a compact cobordism between the zero sets. Right? So that way we would get some sort of unique, well, you know, fundamental cycle if there's no boundary, or, you know, if there is boundary, you know, you get something unique out of this. Right? Sadly, we only really have this for finite dimensional vector spaces. Yeah. And there might be a generalization of this to Fredholm operators in Banach bundles, but that does not help us with our moduli spaces of holomorphic curves, because for holomorphic curves, there's still this Lie group action. Right? And this does not tell us that there's equivariant transversality. In fact, that's just wrong in general. So we want a generalization of this to some sort of function spaces that actually applies to holomorphic curves. And that's sort of, to me, the definition of a polyfold. It's you know, the generalization, the thing that you need to use instead of a manifold in order to get the right transversality package. So, right, so polyfold Fredholm theory with there's a little bit of arguments of sort of mumbling on operations, which I think have not been discussed so much recently. I think that's not really going to be my focus here. But so the big sort of difference is now we're going to want to describe the space of solutions modulo the Lie group and compactified. So this M bar should be the zero set of one section only. So, and a lot of people think that now somehow the zero set is going to be the polyfold. That is not the case. The zero set is going to be a smooth finite dimensional manifold with boundary and corners. What is the polyfold is going to be X. Right. So, and there's a polyfold bundle. That's Y to X. That will be the polyfold bundle, and somehow S is going to be some generalized Fredholm section.
But a manifold is a particular case of polyfold.
Indeed. Yes. Yes. Yeah. Right. So, and moreover, so you actually, so one technique, I mean, you get this all out of one black box that I'll describe. You also get it up to the boundary, so you get boundaries and corners. And you're immediately going to get a nice, if you're using operations, you're going to get a nice fiber product structure on the boundaries. Or if you just think of counting zero-dimensional moduli spaces and sort of using the one-dimensional moduli spaces to get the relations between those counts, you can sort of immediately phrase the relations that you're going to get in terms of the algebraic structure that describes the operations on your polyfold. So that sort of mirrors somehow, I guess, what happened in A-infinity structures, where to some extent I feel somehow the A-infinity algebra came out of understanding how disks can bubble. And that's exactly what happens here, this sort of immediate sort of connection between the structure of the compactification, the stratified structure of the compactified space, and the algebra you're going to get out of it. So. Yeah?
So M bar comes with a smooth structure?
We are going to give M bar a smooth structure, yes.
Out of this?
Out of this, yes. Yes.
And it's canonical?
Indeed, yes.
So no choice? Canonical?
Well, the polyfold, right, the polyfold description is going to be canonical, and I think that, I mean, the polyfold description is not entirely canonical, but it's certainly a lot more canonical than a Kuranishi structure.
The polyfold description of X?
I mean, sorry, we'll get there. So I mean, in order to cut out this moduli space, you could build different X's around it. Right. Yeah.
So M bar you still have the quotient down by the...
No, I have. Yeah. So right. So let's get this sort of back. So M was the old, well, d bar inverse of 0 modulo automorphisms, and then M bar is the Gromov compactification.
But now it's just a pullback section.
It is right. So the right. Sort of classically, it was this much more complicated construction, but now in the polyfold world, right? So this is sort of classical. In the polyfold world, we're just going to do nothing. We don't care about these intermediate steps, so we're just going to write this guy as S inverse of 0. Okay, and so that all sounds great, but what does a user actually have to do in order to get nice stuff? So clearly you have to first understand what your compactified moduli space is supposed to be. Really analytically understand all the possible bubbles. Don't just understand it up to something that you think should be codimension 2 or something. You really, anything that can happen, you have to put into your compactified moduli space. Right? So for example, for me, somehow in all my previous work, there were some weird bubbles. Either I had some sort of bubbles on the boundary of a Young-Mills equations that looked like disks in an infinite dimensional space of connections. And I just really, I didn't want to try and prove removal of singularity for them. I didn't want to even try to describe them. So I just proved that they had some energy and sort of, and so using monotonicity in that energy, I was just able to exclude the bubbling. That's not a setting that I can throw into a polyfold setup, right? Or the figure 8 bubbles that we get out of strip shrinking and quilts. We'd have to actually geometrically describe the figure 8s. And not just say, because of energy reasons, it's not going to happen in the moduli spaces. It's generically not going to happen in the moduli spaces that I'm looking at. So I would need to a priori know that there's, no holomorphic spheres in my manifold, full stop. Then I wouldn't have to include them into that compactification.
Well, I mean, you could still write down a problem, but the third problem would not be, the solution set would not be compact.
Right, it wouldn't be compact, and so we can't run the black box, the red box. So we really need to understand this compactified moduli space, right? Because this is the one we're going to write as inverse of 0. And then we need to make an ambient space X, and write the compactified moduli space as this 0 set. Right? And once we've made that ambient space, we can plug it into an abstract sort of regularizer, right? Sort of a package that makes transversality and implicit function theorems and proves also some independence of the choices. Right? So then this is very much like the finite dimensional statement, except there's some new words in it. And then my goal for the rest of this talk is going to be to explain some of those new words. So instead of a manifold, I now need an M polyfold. And you should think of something bigger than a quotient space of maps. And then there's some bundle over it, wherever the d bar operator goes to. That's your bundle. It needs to be strong, which somehow means that the fibers have some sort of designated subspaces that will make compact perturbations of your operator for you. And then the section, your d bar operator should be scale smooth, which we'll need to explain. Fredholm in some sense, which means there will have to be some filling and sort of generalized scale smooth Fredholm after that filling. Crucially, I think Helmut calls that proper. We want the 0 set to be compact. And then the statement is that there are perturbations. I don't think there is a statement that says for generic perturbations, because there's just no good Banach space, so complete space in which you want to do this. So there are perturbations, and they're so-called SC plus sections. That's exactly sort of lingo for a compact operator. And we'll need to, in a finite dimensional bundle, you could take any perturbation, and you'll get the result independent of the choice. Here, we'll need to restrict ourselves to perturbation that's small in norm and supported near the 0 set. It won't be compactly supported because we're on an ambient space that's locally non-compact. But there are some epsilons here for which you then know that if the sky is transverse, right? We'll pick P so that the section is transverse, and then the polyfold implicit function theorem is going to tell me that the 0 set is not just a finite dimensional polyfold. It will tell me that it's a finite dimensional polyfold modeled on finite dimensional splicings. And that is equivalent to being a finite dimensional manifold. So whatever is, we'll get to the splicings. So it's, there are, we'll also see in examples of the finite dimensional polyfolds that clearly we wouldn't want to get as 0 sets here. So it's important that these will actually be manifolds. It will be compact. It might have boundary and corners. Right. And the thing, so there's the boundary of this zero set is exactly its intersection with the boundary of X. The corners are exactly the intersection with the corners of X. So the whole boundary stratification comes from the boundary stratification of your ambient space.
Actually, in two important cases. One is, of course, if it's in general position to the boundary.
Right.
The other is it actually occurs in SFT because you have all the additional structures to keep. Where you might have something coming out of the boundary, but it has to be not tangent to the boundary. It might come out of corners.
Right. Yeah, there's something, right. But that, I think, there's some bad things happen. But I think that only happens when you try to do this package with operations. Yes. Right, when you're asking the perturbations to be coherent with operations. And here I'm just doing a single perturbation. So here I can keep, what I can do here is, you know, if my ambient space X is this, and somehow the index is 1, then I can keep my solutions set from running into the boundary. That's not going to happen. Into the corner. You know, it will run into the boundary, but it won't run into the corner, and it also will not just end in the interior.
In SFT, because of all the requirements.
Right, in SFT you have some symmetry requirements here.
This bad case will actually happen, but of course, generically that means it just comes off the corner, but it's not tangent. So.
Right. Yeah, so there's sort of some enhanced transversality notions if you want something called coherent perturbations. That's
and that you are able to arrange by choosing a
generic. This here, I wouldn't call it generic. There are P's, you know, and there's lots of P's. Yeah, many P's.
Yeah, I mean, it actually comes in a quite quantifiable way. So there is a norm, and there's a support which is allowed, and if the norm of P is less than 1, it's fine. I mean, it's not generic, but you could, for example, consider combinations like this sum of Ti, Pi, where the T's are squares, have some properties.
Yeah.
And then you could actually make a
and then for almost all T, it'll be, right, yeah.
So there's a fantastic amount of
yeah.
You can actually make countable many conditions.
Yeah. There's sort of one basic problem when you try to talk about generic things is whenever you try to talk about generic perturbations with compact support inside some open set. That's just not a complete space. And so there's no way of talking about generic. Right, or support, sorry, or with support inside some open set. That's just not a complete space. So
but there are so many of these guys that you can build subspaces of this, which are actually Banach spaces or Hilbert spaces, and then you restrict yourself to this.
But also, I mean, I don't really care how many transverse perturbations there are. I just need one. And I need to know that when there's several, I get the same result. Yes. Right? And that's what this says, right? So the last line here says if you have two different such perturbations, you'll actually, the zero sets will be cobordant. And that's.
But in practice, of course, you can never prove there's one unless you prove there's so many.
Well, I've actually, in the Fleur paper that I wrote, we actually just proved that given any one, we find one nearby that is transverse. You know, we didn't prove anything generic there. I mean, of course, we use Sartre-Smale somewhere in between, but yeah.
No, I mean, the solution set is compact. You can linearize it, the solution set, the Theorem operator. Just take finite sections which fill up the Cook. The automatic fill up in the neighborhood. Do extend in some way. Do it for at every point. Since you do it in the neighborhood, you get a finite covering. So there are finite many sections. So you get the sum SITI. Add this to the Fredholm thing. It's another Fredholm thing. And solve. Look at all solutions T, X that this perturbed thing is solved. Then you actually have a finite dimensional reduction. And the map onto the parameter space T. Take any regular point, there's a regular section. So it's reduced to the usual sum.
Yeah. Okay, good. So, right, so I owe you a lot of language now. You've seen the main theorem, and now you need to know some language in order to be able to apply it. And here's sort of first the ideas. I think to me there's sort of two germs of ideas for the development of polyfold theory, and somehow the rest you could do yourself, given a lot of time and patience, right? But there's sort of no more really deep, I mean, also daring ideas. There's two very daring ideas, and then the rest sort of just comes from, redoing functional analysis and differential geometry based on the daring ideas. So issue number 2 that we'll talk about second is that when you're trying to describe this space of maps, modulo automorphisms, that you're trying to cut your holomorphic moduli space out, if you're doing this in charts, somehow the dimension jumps over the boundary. Because in order to describe, so on the boundary you'll have a nodal curve, so you have 2 maps from a sphere, essentially, and in the interior you just have 1 curve, so 1 map from a sphere. And so that looks like on the boundary you need twice as much data to describe your maps. So it's going to be impossible to give that a Banach manifold chart.
Yeah, so technically
And so,
the boundary looks higher than
right?
that.
Which is kind of weird. And so that leads to the idea of splicing cores on which both the polyfolds and the bundles will be modeled. Oh, right, I didn't say that explicitly. So M means manifold flavor. There's no symmetry of your automorphism group. So if you want to deal with finite isotropy groups, you just drop the M and think of everything in a groupoid setting. And then everything is a polyfold, and your 0 sets become branched weighted manifolds. And you cuff a little, and but you get a similar theory, which I think if you understand how to get from a manifold to an orbifold, you can understand how to get from M polyfold theory to polyfold theory. So M polyfold theory is a thing that's hard to wrap your head around. Okay? And also much belabored in the last couple of days, problem number 1 is that the reparameterization group here, this automorphism group that we're quotienting by boldly, does not actually act smoothly on any infinite dimensional space that I know of. And here's sort of the baby example that I think is going to be relevant for Peter's Morse theory case, right? So C1 functions on the real line that I might want to shift by a real parameter, right? So tau and u goes to tau star u, which I just get by shifting with tau. Innocent little action of the reals, but when you take its differential as a map from R times C1 to someplace, you get an expression that involves, so you take it at the base u0, you get an expression that involves the derivative of u0. So if you see 1 here, then the result is going to be C0, which does not get you into the tangent space to C1. Right? And so, in order to get into the tangent space to C1, you need to take your base point to be C2, and so on. You can play the same game. Right? So it's not even differentiable. It's not even continuously differentiable on C infinity. Right? It's not differentiable on any non-smooth, on the generic points in C1. So this first issue led to the first dramatic idea of just redefining the notion of smoothness so that this guy is smooth. I think that's essentially. There were 2 competing requirements. On the one hand, we want this guy to be smooth, and on the other hand, we need the chain rule, at least. And so I think that's probably how Helmut et al. Came up with scale calculus. Okay, so maybe one day, at least our math students won't take calculus in their first semester, but scale calculus. Well, that would maybe be a little too much. But, you know. Second semester, I think you'd be quite ready for scale calculus.
Both from your in the second semester undergraduate you did elliptic estimates.
Yeah.
Who did? Jürgen Jost.
Oh, and that's actually, that's...
Space and everything was already done the first semester.
And then they make you director of the Max Planck.
Yeah.
By the end of the first semester, he was left with one single student.
Ah.
Which was you, right?
No, which was casting
No.
plus.
Ah. So elliptic estimates is a good sort of keyword actually. So when I first saw scale calculus, you know, it took me a moment to sort of wrap my head around all the indices, but then I was like, oh my God, this is exactly what you want to do when you're dealing with an elliptic operator. Because an elliptic operator maps elliptically between Sobolev spaces, you know, W2p to W1p, for example, the d-bar operator, but not just from 2 to 1, but from 3 to 2, and from k to k minus 1. And that is exactly what's going to happen here. So, right, so functional analysis 2.0. Banach spaces are not good enough anymore. We need a scale structure on them.
Of course, I mean, scales was of course known in interpolation theory, but they never interpreted it as a
Okay, good. Right, so a scale structure is a sequence of subspaces, but not with the subspace topology. You give them their own Banach norm. So that E0 is just takes the norm of E and is, you know, exactly the whole space. And for all higher M's, the sort of inclusion, these are nested subspaces, and the inclusion should be compact. And it's also going to be dense momentarily, but we don't need to assume that for everyone. We're just going to assume that the intersection over all of them, E infinity, is dense. So.
Compact is a compact operator. Yes.
Right, this is a compact operator. Right, yes, yeah. Yeah, sorry, the inclusion is compact, right? So not quite an example is the CM spaces on the real line inside C1. Yeah. E infinity is going to be the smooth ones, which is nice and dense, but all these inclusions are only bounded operators because you're on the non-compact real line. So if you did this on S1, that would be a first example of a scale structure. If you want to do Morse theory, you have to do it on the real line, and you could take something like Sobolev spaces, and then you can sort of make up for the non-compactness of the domain by throwing some exponential weights in. That I don't want to. I'll leave that to Peter. Yeah, someone has to do that. There's a little bit of hard work, but not. Yeah. Okay. And now we get to define what it means to be continuous. So E now is a scale Banach space. F is also a scale Banach space. Now a map is continuous if restricted to each level. It sort of preserves the level and is continuous as a map between these normed Banach spaces. Okay? Right, that's exactly what elliptic operators do. You know, except if you had if you had the d-bar operator, it maps W1p to LP. Just means you take different scales. Right? So F1 then would be W1p, whereas E1 would be W2p. But nobody told you that you have to take the same differentiability as scale on your Banach spaces. Okay, and with that, at least, well, time shift is actually continuous, which is not entirely trivial to prove.
If you write that, if I wrote it out without assuming anything except Hölder inequality, it would be nearly 2 pages.
Yeah, yeah. So, and now it gets interesting, right?
Let me paper, there are papers actually in the literature proving something about Compactness where they say it's C1.
Excellent.
Obviously C1. They didn't
Yeah.
dare to say it's obviously C infinity. But it's not
Yeah.
even C0 in some sense.
Yeah. Yeah, well,
But that's it by the old times. Meanwhile, I think everybody knows.
Okay.
That's it.
good. So now comes the interesting thing, right? So we want this time shift to actually be differentiable. So we're going to make a notion of differentiability that it will satisfy, hopefully, right? So we need it, right? So remember, I guess, let's see. Yeah. Oh, different. Well, other people can't see you there, but okay. So let's see. What was that again? Tau comma u maps to u of tau plus dot. And the issue with sort of delta tau and delta u, so the differential at a base point, say even 0 u naught, the issue is that that maps to something that involves u0 dot. Right. And so, right, so if u0 is in C2, then this actually maps C1 to C1. And that's exactly what's going to happen here. So, well, this is sort of a little weaker. As a map from C2 to C1, it's differentiable. Right? And then we'll have a differential, but that differential would map E1 to F0. And we're going to ask, because we want the chain rule, I think, that this differential actually extends continuously to E0. And that's exactly what happens here. The issue is not in the delta U. You know, that delta U just comes in, I think, with a delta U in this case, since I'm shifting by 0. Right? So it's perfectly linear on delta U, and it maps C1 to C1. So the differential extends as a linear map on C1. Right? So that's what happens here. And it extends, and we would like it to be, as this operator, we would like it to depend continuously on the base point in E1. Right, so this linear operator here now depends continuously on U0 in C2. Right? And that's exactly sort of the content of saying, just sort of writing down the tangent map to this, that sort of phi and d phi, and say that as this whole tangent map, this should be SC0. Right, and that means also, right, by saying SC0, that also means it is, you know, it has the same behavior on all other levels. And so that essentially also was the sketch of why the shift map.
There is this shift of index.
Right, right. So the base point is EM plus 1. The fiber, that's sort of the tangent direction, is EM.
That's by definition the tangent space.
Right, yeah. So the tangent space now to C2 is just C1. By definition, right. So that's sort of a scaled tangent space somehow. Right? Yeah.
What's the role of the deltas forming the strictly increasing sequence? Where does that?
That gives you the compactness of the embeddings. Yeah.
I mean, you have local compactness by Sobolev embedding theorem.
Right, and then you need to control the tail.
It's
That's
stronger control
yeah.
than makes it sort of very compact.
okay.
So what is the
Yeah.
exact definition of the tangent space to the scale?
It's right. I didn't exactly say that. Right. So this tangent. Oh, right. So the tangent space. Okay. Yeah. Let me try and say that. So T indeed. T E is E0 times E1 with scale structure EM times E1 times E0. With scale structure EM plus 1 times EM. Right, so this is the vector, and this is the base point. Okay. Yeah, I guess I used to not like that notation, so that's why somehow didn't make it onto my slide. Okay, good. But the meaning really, I mean, the meaning really is that you need all these maps to be, standard continuous operators. So we've defined SC0, we've defined SC1, and now we can just iteratively define SCK. And that's where it's important to have this whole tangent map, because it's SCK plus 1 if the tangent map is SCK. Right? And it's scale smooth if it's SCK for all k. And so you can just iteratively go through the time shift and check that sort of by induction, all that is true. And that's, right, that's what I'm saying here. This is the time shift. Everything is fine. And we've, I'm sure they, played with these definitions a long time to get the chain rule. But once you, and that's where the compactness is crucial, I think. Good. So that's scale calculus for you. Now you have a chain rule.
You should point out the same chain rule is a little bit of miracle.
Right. It goes, you keep going down. Right. It is a miracle. Yeah. So, good. And now you can define what linear Fredholm operators are, and yeah. Oh, because I mean, you compose things that keep going down that lose one derivative somehow. But when you compose them, the composition does not lose two derivatives; it just loses one. So
differentiability says you can approximate like this by linear map.
Yeah.
If you take a composition, you would go 2 steps down.
Exactly. But you need to go just one step down. So, and if you want to see the miracle, try and prove this by yourself. Try and prove it without assuming this compactness.
Compactness allows you to go.
Yeah, to
Yes,
lift yourself up again. Okay, so that was the easy part of polyfolds, I think. So, so that's the part that would allow us to do analysis on a space of or a space of maps of some Sobolev regularity modulo the automorphism group, which is already pretty nifty. But really, we want to do analysis on a space of nodal maps with different domains. And so that's where, right, I'm not going to talk about SFT. So you need we know that we needed gluing to understand nodal things, and now we're going to need anti-gluing to make these to make gluing into a decent chart map for a polyfold.
Can you remind what problem 2 was? One was
Problem 2, right, problem 2 was that we needed to compactify, and there's dimension jumps going on that come, near the. I mean, problem 2 is really that you want nodal maps and maps in one space, and you want to give it the structure. Essentially, you want to give it some smooth structure. Yeah. And this was where, essentially, somehow they said, well, we have the pre-gluing construction. It's not injective, but let's just make a definition of a chart in which the pre-gluing, although it's not injective, is a chart. And then, let's see what we need to do in order for that to still satisfy some implicit function theorem. So let's see. Right, so I'm essentially sort of already doing half of Peter's work here, but I can be sloppy because he's going to be a little more precise. So we would like to make charts for a space X that contains broken as well as unbroken paths in Rn. Because then, my operator, my section is going to be the gradient flow equation. So these will not be Morse trajectories. They will just be smooth maps or continuous maps into Rn. Right? And I'm going to assume that I just want to really describe the neighborhood of a broken path, so something from the positive real line that sort of converges to 0 at plus infinity, together with something from the negative real line that converges to 0 at minus infinity. Right. So I want to describe a neighborhood of this. Right. This now is one point in my polyfold, and I need to make a chart nearby. And there's different kinds of objects nearby. There are unbroken paths. And these now just have a specified length because I had endpoints here. And there are broken paths that where I just wiggled the path to 0 a little. The nice thing here is I can't break anywhere other than 0. When you do holomorphic spheres, of course, you have to your nodes can be anywhere.
Which is sort of the Morse situation.
Right. Yeah. Which is a little more pesky to understand. And also note I haven't quotiented by R here because I don't want to put in hypersurface conditions. That's just painful. So this is what the obvious thing to do, and that's what we used to do in our gluing analysis. We'll take some gluing parameter. Somehow I think of gluing parameter 0 as really infinity, so I need some sort of translation between small numbers and large numbers. This translation is called the gluing profile. And then I'm going to glue pairs of maps from positive and negative real line into some paths. Right? So X is my space of paths here. And the way I do that is H is how I wiggle the U0, K is how I wiggle the the V0, and R is my parameter. So when R is 0, that means I'm not gluing. This is just sort of the pair of unbroken guys. That would be this here. U here would be U0 plus H. V would be V0 plus K. Right? So I just have a pair of paths. And when I have a positive gluing parameter or a finite gluing length, capital R, then I'm going to do the same thing. I first wiggle, but then I'm going to do an interpolation that goes along the green line and then sort of interpolates near 0 and then goes out along red. So let's see. Right, this is going to be surjective because that's how we define our topology. It's locally surjective, but it's clearly not, it's just not going to be injective, because you forget everything that happens near 0. But, right, so the idea of this, we do want to interpret this as a chart, though. And the way to do is to find some subset of this large space from which it is injective and still surjective, right? So it's going to be a homeomorphism here. So this is going to be my polyfold chart. And now I need this space down here to not be completely crazy. Right? It does sit in a Banach space, so that's already nice. But I would like it to be some kind of controlled subspace of a Banach space. And nowadays, in general, it's going to be the image of a retraction. I still prefer the language of splicing cores, and I think it's sort of easier to understand. what's going on. So, because for every gluing parameter, I can look at what this map does. For gluing parameter 0, it actually is injective here. So for gluing parameter 0, this fiber here should be the whole space, because that's where things are homeomorphic. But as soon as my gluing parameter is non-zero, I will want to restrict to some subspace on which it's injective. And what I'm going to do, so this should be a complement of the kernel of this operator, the plus. And there's going to be a minus gluing that's just going to be complementary. So I can take the kernel of the minus gluing as this complement. So let's see what that is. So sort of very sort of purely linear algebra, what we need here is a map. We need to make a product of maps that is an isomorphism. Then the kernel of this map is going to be a complement of the kernel of that one. And the way to do that is to just look at the either look at the formulas or at the pictures. So they're both here. Maybe in pictures, what happens is that this part of U gets remembered by the plus gluing. And there's an extra part, there's some interpolation going on. There's this infinite part, I need that to get remembered by the minus gluing. V, some part gets remembered by the gluing. The tail I want to remember by the minus gluing, and somehow there's an interpolation between the two, and I need to sort of remember somehow complementary data of that interpolation. And so algebraically, the way to do that is we have a cutoff function that does this interpolation here. And this is sort of the first line. That's the gluing, cutoff times U plus 1 minus cutoff times V. I need to shift V a little so that I get things actually on the interval. And so I just need to write down some matrix here that's invertible, right? If I wrote 1 minus tau and tau again, I think that would not be necessarily invertible. But I just plug in a minus sign. Yeah. And that's the weird thing that happens here is this tail here gets remembered as minus U. But why not? Yeah. But really, this matrix is invertible, and so that gives me an isomorphism. And somehow, more geometrically, what's happening here is really there's sort of, this is the gluing, fine, right? And the tail of V gets remembered, but the tail of U gets reflected up here. And so the minus gluing actually is a little loop sort of near this one that sort of, sits sort of somewhat far away from the plus gluing. It's not just a loop here. You could reflect it down, I guess, if you wanted to. But okay. So that's plus and minus gluing, and so I said we're going to use the kernels of the minus gluings as sort of the domain of our chart. So.
The target of minus gluing is match defined on R.
Right.
R.
Yeah. Yeah.
Which I should imagine as living only very, very close to the axis.
Yes, actually,
Right. Yeah. There's sort of a little.
Space at the
Right. They map to the tangent space. Right. So it's a little weird. This is sort of a family. In my setup, there's sort of a family of maps that maps to a family of targets. The minus gluing always has domain R, but the plus gluing has domain that sort of gets longer as R goes to infinity.
Yeah, so in
But,
the manifold setting, the first defining interval would go into the manifold,
Right.
and the other one would go into the tangent space over the critical point.
So that was sort of the geometric intuition where splicing core came from, and now we're going to formalize that. So here's the, yeah.
Provide some
Yes, it will. It's gonna. It's, to me, I think a splicing is some sort of generalized fiber bundle. It's just that the fibers are not constant in dimension.
Does that exist in real life as a word?
I don't. Huh.
Some log wood.
So you just split it. You split. So
That's splicing.
Huh. Yeah, but I'm not. Yeah. Huh. Oh wow. Right. So formally here, right? So the splicing. Well, let's see. Right. Yeah. Let's just go through this. So splicing consists to me of some open set of gluing parameters. In our case, that was just some real parameters. A Banach space with scale structure. That was the spaces on the positive and negative real lines. Scale structure. Some exponential decay Sobolev spaces. And now a family of projections from gluing parameter times my space to my space. And I'm asking that family to be scale smooth. Right? So what I'm not asking is the map from V to linear operators on E to be even continuous. Because that would imply that the images of the projection are isomorphic. Right? So this is some weakest sort of continuity for this operator. Actually, I think it's called the strong topology.
Can you repeat what you do not require?
I'm not requiring the map from V to linear operators on E to be continuous. Right. No interesting splicing has this map continuous. And what's happening here is we're projecting onto the kernel of the minus gluing. There's your formula. You get some atrocious thing. Note that it does involve shifts. So this is only going to be scale smooth, not smooth. And then the splicing core is simply the family of images of this projection. And so in the case of the gluing and anti-gluing, you have your gluing parameters, the kernel of the minus gluing, which for gluing parameter 0 is indeed my whole space. That's what I wanted. And for positive gluing parameters is something that I don't quite know. I mean, it just doesn't look pretty. But when I apply the plus gluing to it, it makes it isomorphic to maps on this line interval of length r. And that's exactly the data that we need for our chart. So, right, and with that, right, I can, if I restrict now my plus gluing to the splicing core here, I actually get an injective, surjective map. And yeah. So that will be my chart.
So splicing cores are your chart.
Right, well, there is, no, that's always somehow the case.
Actually,
So
Katrin for some reason likes splicing cores and
yeah.
I like retraction. So this is a particular case
Of a retraction,
subset,
right?
Which is the image of a smooth retraction.
So this is your splicing core here. The family of projections is a retraction on this Banach space. And in some sense, the chart is the map from this image of that retraction. That's a homeomorphism. But you very crucially remember the data of that retraction and the ambient space. So it's very much like Kuranishi structures, where you don't just remember the somewhat weird space that you need to, for your chart. You remember a nice ambient space with better structure.
Yeah. So what I like, I mean, in whatever actually thing you do, you get this kind of thing. But from a philosophical point of view, it's nice to think about this retraction. So retraction is a smooth map with R composed R is equal R. Since you have the chain rule, TR composed with TR is TR, so the tangent map of the retraction is a retraction. And then you can show, which is easy to show the following result, if you have a subset, which is the image of a smooth retraction, they take the smooth retraction of the subset, takes a tangent map, and applies a tangent map, so TR to TU, and you get an image. And this subset which you get in the tangent space is by definition the tangent space of this retraction, and it doesn't depend on the choices. It comes from the geometric property of being a retraction. So what happens is
let me finish something.
Models are retractions for the geometry.
Yeah. So I want to get to some baseline of actually defining an M polyfold, and I have more, but slow insight is best insight, I think. So now we just copy the definition of a manifold. We start with a second countable Hausdorff space. We say what a chart is. Right? So a chart is a homeomorphism between an open set of X and now some open set in a splicing core. And now we need, here comes the magic, really. In order to say what it means for these two charts to be compatible, now we don't need some charts like in Kuranishi structures. So this compatibility is going to be, right, that's a little nasty. So U1 and U2, so this is an X, that's my overlap. It gets mapped to from some open set in the splicing core. That splicing core sits inside a scale Banach space. So there's a projection down to that splicing core. And now I need to go to the open set. So here's an open set in a scale Banach space. It gets projected to an open set in the splicing core, gets mapped homeomorphically into X, gets mapped homeomorphically back out into a splicing core, which simply sits inside another scale Banach space. So I'm souping up my actual transition map by the projection and the inclusion to get a map between open sets of scale Banach spaces. And I can ask that one to be scale smooth.
So there's no choices involved.
Right. Yeah, there's absolutely, well, there is a choice of the projection. But the projection, in fact, right, the projection is part of the data of the chart, right? Because there's a splicing core. So really the chart has that projection. And right, unlike Kuranishi structures, we don't restrict, we don't construct some chart. We just on the nose say what it means to be compatible.
And that even true in the retraction picture, it doesn't depend on the choice of the retraction as long as it has the image and it's smooth.
Right.
So
And then
stronger than assuming that just the transition maps
what do you mean? The problem is what do you mean by smoothness on a perverse space? Right. So, right. But once you have these two notions, you can just again, copy your definition of a manifold and just say that an M polyfold structure is an atlas, a collection of compatible charts. Yeah. And I would venture to say that when you do Morse theory, essentially any charts that you write down are going to be compatible with each other. The only choice, I think, is the gluing profile, which translates small numbers to large numbers. So there's one real function that could make charts not compatible. Will make. In fact, it depends on the function. If you just add a constant, you're fine. But so if you make your charts with the same gluing profile, I can't prove it, but odds are someone's going to prove it. So in some sense, there actually is a canonical M polyfold structure, at least for most trajectories, probably for most holomorphic curve moduli space problems. Right? And so you don't really need to worry about what happened. There's no choices in the description of the ambient space. The only choice is going to be in the perturbation. But we have a cobordism theorem for that. So, okay. Yeah.
In this definition, what is the tangent space at a point?
The tangent space. Ooh.
Take a point in U.
Yeah, there's, here.
Yes.
Well, there's a tangent space to a splicing core, which is somehow the image of the differential of the retraction.
Of the projection.
Yeah. But you somehow you don't really need that, because whenever you think about differentiability, you actually think about the map from on Banach spaces.
When I think of tangent space, I have to think of a scale.
Yes, you think of the scaled tangent space
you
here.
can find a tangent space at points, at least on level. First of all, since you have this filtration, this manifolds get a filtration for the integrals.
Yes.
And then if let's say the smoothness of a point. So if the smoothness is at least 1, you have a tangent space, and you take the usual definition, which you take for Banach manifolds. You take a vector, the tangent vector of the chart, and comma the chart map, and you define the equivalence relation that two such tuples are equivalent, provided the one vector goes to the other one via the tangent of the transition map. You do the same. And you have a tangent for, because if you have a retraction, the tangent of a retraction is again a tangent. So that is again a retraction. So there's a notion of a tangent for the local point.
So this retraction is very simple, right?
Yeah,
You just take the image out of the tangent map. That's the tangent.
And when you talk about retraction, you're talking about scale smooth retraction,
Yes,
right? Yeah. And when I think of the image, I have to think of a scale smooth Banach space. Yes.
Always, yeah. Everything is scale smooth now. Yeah.
Think of it as kind of this ladder of Banach.
Right.
Yes, that is part. I mean, for many things, you don't. What is smoothness? Smoothness is some taming device saying that a map isn't too bad. Yeah? Some notion of smoothness for most purposes. Then, of course, you can do certain things like tangent space and so on. And for most practical things, is that you can do certain things and just say certain things behave nicely. Yeah. But it doesn't even appear. I mean, they're in the background, of course. But
Yeah.
for many things, that wouldn't even appear.
I guess one thing I forgot to say is when you're on a finite dimensional a finite dimensional Banach space, right? The canonical, the only scale structure on a finite dimensional Banach space is E. Because finite dimensional subspaces will not be compact unless they're will not be dense unless they're the whole space, right? And then the notion of scale smoothness, right? Yes, and then the notion of scale smoothness is equivalent to standard smoothness. So that's right. And so, yeah, I thought, well, I'm done. If you want to see more pictures, you need to ask more questions.
Well, you can explain this picture.
Sure. Right. So yeah. So this is an example of a polyfold in finite dimensions. Right. This is not going to be relevant for holomorphic curve moduli spaces. Open annulus and a line attached to it. And there's a simple chart for an open set in here where your splicing is just the project. R2 is your Banach space. The splicing is the identity. The image is still R2. You take an open set in here, have a homeomorphism. And then there is a fundamental example of a splicing in L2 where you have for the projections have image a line, and then that line converges out to local infinity, right? So base vectors turn and converge to 0 in the weak topology, and then your projection continues as 0. So fully prepared, right? So E is L2. There's a little bump function. And I'm going to define just a sequence of functions. They're going to be 0 for negative gluing parameter and the bump function shifted for positive parameter. And as parameter goes to 0, bump function is going to go out to minus infinity. Right? And then the operator is the projection to the one-dimensional space spanned by that bump function. Right? So what really happens here is that these lines are not the same. Right? There are times this bump function. Right? And as you got in here, the bump function converges to minus infinity, so somehow projection from an L2 function to it converges to 0. So, yeah, oops. It's time. Yeah.
So the previous example was an annulus with the curve.
Right.
So it's an open annulus, right?
It's the open annulus, right? Because in this splicing core, this line here is not there. That's already 0.
So my question is, can you give more examples of this nature? I mean, how complicated can you make a picture like this in 2D?
Well, I think if you're doing splicing cores, I think 5 years ago I sat in Washington Square Park and tried to see what the examples are. And I think I realized that if you restrict yourself to a two-dimensional picture, this is the only non-trivial splicing core.
But how could you have them clustering?
I don't think so.
You don't think that
I mean, this is a family. Here, what I'm plotting here is a family of vector spaces. And what else can they can jump from one dimension to 0, and they only jump down in dimension. Somehow, you can check that.
But
So
the global picture can have many.
yeah, the global picture could be, totally crazy. Yeah, I could have stuff through, right? Because all I do is, a little neighborhood of this weird point. Now I can give good structure. This is finite dimensions, but I can give it a good structure by making a homeomorphism to this splicing core. And this sitting in this large Banach space, L2 times the real line.
So Katrin,
Yeah.
do you see that they cannot keep jumping up and down, so you get interval 0, and it accumulates?
No, but there's this example where
Does it
one
that it
fiber is
accumulates? Oh, only
Yes,
one
yes,
fiber.
There's an example where just
Ah.
the line at 0 you
Or
take
then
out.
you can take infinitely many
Ooh.
of those guys.
Yes.
Probably.
So in particular, you can
No. Okay. Yeah, sorry. Okay, so there's one more non-trivial example.
Because, I think it can be rather weird to make an angle constant.
put R2 minus the real line and put in 0 again.
Yeah, so that's this space. Right, you're right. But I don't think you can make them accumulate because I'm pretty sure that the dimension of the fiber is something lower or upper semi-continuous.
But there's
It can only jump down.
What's the tangent space, the point where they meet?
Something in here.
No.
No.
Okay, so
I mean-
if you could give a classical description of this. You take the open half plane and you stick an interval in. But then you have to sort of give the infinity jet how you stick it in. Yeah. And of course, it doesn't matter how far you stick it in, so it would be an equivalence up to sticking it in to something. It's an equivalence of data how you stick it in. You could stick it in like this, or like this, and so on. And it doesn't show up in the formalism, but it keeps track of it. So the formalism is as easy as it could be.
Yeah, I think so. So in this picture, that's the one interesting place to ask for the tangent space, and it is one-dimensional. It's just 0 times the gluing parameter.
So what is the answer to Martin's question? Sorry, it's just one dimension. There.
But there's-
If you stick
Yeah,
it
yeah.
there's
At this
one
point,
dimension everywhere else is two
at this point, it's just one-dimensional. Yeah. Good, right? So you describe this whole space, and then you could run a Fredholm section on it, right? So this is my right. So if you now wanted a Fredholm section on this thing, you'd need sort of compatibly jumping dimensions of the fiber. So this is an example of what a Fredholm section of the index 1 would look like. You'd need to, over the two-dimensional part, you'd need fiber R, and over the one-dimensional part, you'd need fiber 0. And then if it's transverse to 0, it is going to cut, this is all going to be 0 set here, and it's going to cut, it's going to come in here, and you don't know how you're going to get smooth structure here. But from your ambient space, it's going to come in and just continue as a one manifold, do something in here. So the key is that from the big infinite dimensional ambient space, you get smooth structure at these weird points. Yeah.
The jump could be from infinite dimensions to
Also.
Yes. Yeah. Yeah. And you know, in holomorphic, I mean, in the actual applications, you jump between different infinite dimensional spaces. That's pretty much all that ever happens.
And you can jump actually from infinite to finite dimensions.
Right.
So, which might be used for, and you could have a Freitas theory
Right.
to combinatorics, for example, if you find a good degeneration.
Right. Yeah, I've been thinking about that a little. It's sort of, you know, the adiabatic limits that I would like to do in polyfold setup are somewhat complementary to what's happening with the gluing. Because in the adiabatic limits, you usually sort of, as you get to the boundary to, you know, adiabatic parameter 0, you lose dimension. Right? So if you try to, whatever, you know, degenerate, say, Hamiltonian Floer theory to Morse theory by throwing an epsilon on the J or something. Right?
But
You somehow, in the limit, you're losing dimensions in your ambient space, and so that's sort of that's clearly not a splicing core. Yeah.
Yeah, but you could do some other things. You have you start with a Freitas problem, and then you cut sort of down the dimensions of your bundle to finite dimensions, and end up with a finite dimensional problem. I think you can do the same. I think you could go, say, from an infinite to a finite dimensional problem.
Right, but again, you know, that's sort of your.
Yeah, but it might be different.
You're jumping up in dimension there. You know, from the boundary into the interior, you're jumping up in dimension rather than down.
Yeah, but the thing is, if you have an infinite dimensional projection and take, say, this finite this infinite codimension, then if pi jumps up, then if you look at identity minus pi, you actually jump down.
Right.
So you have both phenomena in infinite dimensions. So if one projection jumps up and you take
Okay,
then
right.
it jumps down. So
Yeah. Yeah.
So you have that.
Okay. Yeah. Okay. Oh, sorry. Okay. So it can be a splicing core. Okay.
Yeah.
Okay.
It can be, yeah.
But it's just somehow very unlike the splicing cores that we've used so far.
Yes.
Yeah.
So,
Right.
So there are other models
Right.
as well.
Okay. Yeah.
Thank you very much.
Lunch.